Hello, this is a video walkthrough for exercise 3, the traffic light exercise for 7575. And so, like with all of the others, uh, we're just going to start by creating a new project. So, again, name your program, and the program language is LD. Okay. So, this lab is a little different than the ones in the past, because there is no clear instructions on the exact specifics of what you need to do. It's just stating parameters, and as long as it meets those parameters, it's completed. So we're going to start with the variables. So the first one, we're going to go through our lights. So we have our north-south section, and these are booleans with a location of qx 100.0. Okay, and then we can go create another one. And this one will be yellow with a 0.1 address. And the green with a 0.2. So now we go through the other lights, the other stack of lights. So we have east-west, red, and this location will be qx 0.0. This is like this so we can actually access it via the HMI later in the lab, but these points are different because these are mapped to the actual board, and since we don't have enough inputs to do both sections, these three will have to be solely in the HMI, and so that's why their addresses are different. Okay, so there's our 6 lights, 2 for each stack, or 3 for each stack. And now, for my build, I created 6 other variables of type integer to record the time for a timer. So I just named them time and their respective color and location. And these will have a register address. So it's the NW starting at 0. Okay, and so these are all the variables that I used and their locations. So now we can go ahead and start with our drawing. So for my build of this project, I basically built a 1 circuitry for the north-south stack and 1 circuitry for the east-west stack that were basically just inverses of each other. Uh, so whichever variables I used for north stack, I would use the opposite variables of the east-west stack. And this is by far not the only way to do this, or probably the most efficient. But I went and started with a left power rail with 7 pins. And following the structure of a normal street light, let's start with green on the bottom. So in the documentation, it said that green can only be on when the opposite stack red light is on and the opposite stack yellow light is not on. So we're going to create a normal contact for the opposite red and another negated contact for the opposite yellow. And when going through this and building your own logic, you can look at the wording of the parameters. So like I said, the opposite stack red and yellow light. So you might foresee that you need an AND block. And I would recommend just going to bitwise and AND, because if you search it, it'll bring up a whole bunch of other stuff. And just connect them together. Now, originally, I had connected this straight to a green light coil, but through testing, I realized I needed another step, and that was to create another AND block. And connect the output of this directly into that one, and come down here, create another left power rail with 1 pin, and connect it to a normal contact, or no, a negated contact for this stack yellow. Because otherwise, you'll have both green and yellow on at the same time. And this can connect to a coil, a normal coil for north-south green. And then that can connect to a power rail. And there is my green light for the north-south stack. So now on to the yellow light. And as we move up, these will get a little more complicated because they have more requirements. And so, starting from the beginning, we have another same parameter as last time, so normal, not the opposite red. Because we don't want that side going while this side is also going. And then we'll also have another contact for the opposite side, green and yellow, negated. Okay. And another AND block. And connect the green and yellow to that AND block. And we'll need another AND block to connect the red coil, or the red contact, and the AND block we just created for the green and yellow. And this is where we want to put our time. So we want to wait 10 seconds after the green to turn on the yellow. And so we'll want a T on block. With the input being the output from the and the PT as a variable with the expression capital T number sign 10 seconds, 10s. And connect that to PT. ET we will actually be using later for displaying a timer. And we'll actually need another AND block. And I only discovered this through building and testing. So in input 2, we'll put Q. And I'll come back and get input 1 when we do red. And output goes into a coil, a normal coil for NS yellow. And that goes into a power rail. So there's yellow and green. Now all we need is red. And so we're going to start with the opposite green and yellow. And these have to be normal. So if the other light is green or yellow, we want this one to be red. So green and yellow. But this one is not an and. We want this light to be red if green or yellow is on the other side. So we'll have an or block. And connect those two contacts to the inputs. So moving on from this, there are actually two conditions for where this stack red light will be on. It's, for safety reasons, it's either the green or the yellow on the other stack is on, or 5 seconds have passed since our yellow light has turned on. And so to do this, we'll actually need another or. So another or. And with input 1 being the output of the first OR block. Now, the second input is going to be from another T-on block. And so we want the red light to turn on 5 seconds after the green light or the yellow light turns on. And so we can take this Q value from the first T on and put it into our input. And like with the first one, we can have a variable with T number 5s for 5 seconds. And we can put that into PT. ET, like I said, will be used later. And I'm actually going to move this back. and redo this just so it looks better. Okay. And so another issue that I found when testing my original designs was that the red and the yellow light would stay on. And so this is why we have this this third and block in the yellow scheme. But we want Q to come into here, but negated. And Q can also connect to this OR here for the red. So if we create a block and we search not a not block, it will actually flip the signal. So coming in, oh, that's ET. Oh, that's not what I wanted. There we are. Q down to the not, and this not into input 1. And so coming back to complete the red, this goes into a coil for a normal north-south red. And that connects to a power rail. Another issue that I found was that when we set EW red to true, it would never be unset. So also when we turn on this red, we also want to come up here and connect it to a reset coil for the opposite red. And connect that to a power rail. So here's the basic circuitry you'll need to make one stack work. And you can just select it all, copy, scroll down a little bit and paste and change all of the variables to the opposite. So if it were east-west, it would be north-south for this second. And then it should go through and act like a traffic light. But one of the other parameters for the assignment was to have a timer for each transition. And so I actually found this to be the hardest part until I thought of a way. The way I did it was I took only timing whichever light was to come next. So if green were on, if north-south green was on, then the timer for north-south yellow would be start counting down. And then once that turned on, then the green for the opposite stack and the red for the current stack would begin counting down. And so to do this, I'm going to start at the yellow T on block and connect it to a block, but this will be a time to int. A time to end block. And this will basically convert the time from ET into an integer. And then we can connect this to a subtraction block. And the output of this into a variable for the corresponding light. So this would be for time NS yellow. Oh, and I forgot up here the variables. The time variables need to be an integer. That is why, well, that is why you saw the red line when connecting the output to the block. Okay, so there's that. So see, it's no longer red. And so then in input 2, we want another variable with the expression of 10. So basically what this will do, this tone block will start counting upwards from 1 to 10, or 0 to 10. And so ET will begin to grow from 0 to 10. And once we convert it to an integer, I actually need to switch these, because in a subtraction block, it's input 1 minus input 2. So yeah, so ET will output increasing values from 0 to 1 or 0 to 10. And so if we take 10 and subtract that value, we will have an integer value representing our time counting down to the transition. So once the NS green turns on, this begins counting upwards to 10 seconds, and this every second will subtract 10 minus whatever second we're on and produce a countdown timer for the yellow transition. And so we're going to want to do the same thing for NS red. Although this one will be a little bit different. So connect that to input 2. We have a variable, this one with an expression of 5, because we only want 5 seconds in between for that transition. Now, this will not only output to the time for NS red, because this also applies for the time for EW green. For time EW green. And that's because as soon as this red light turns on, the green light on the other side will turn on. And so the countdown timers will be the same. And so now we can literally just copy this and paste it and move it down where you can separate them. And then you can just go through and change all of the variables to the opposite stack. So east, west, green, north, south, green. east-west yellow, north-south yellow, and so forth. And you don't have to change any of the negations. Okay. Now, once we've done that, um, we can test it. So click the running man up there and wait for this to say PLC started. And hit the sunglasses. And here's our circuit. So if we come here in one of the red variables and force it to be true, and then release the value, you can see it's counting up to 10, then it switches, then 5, and it switches, and down here our green light is on. It's counting up to 10, then yellow, 5, red, and green. And the time, as you can see, is slowly counting down. From here to 1, then transition. So before saving and generating the file, we need to actually go into one of the red lights and actually set it to be true, because we need to be able to find it later. We need to actually have this running, and we can't do that with the HMI if we can't find the variables. And so for me, I would just go to EW red and set that value to true. And if you can't do this, if it's giving you the error, like I said in the previous example video, go back to OpenPLC project, go to runtime, and then Windows, and you can download it there. And it will actually download and install all of these. And that's just the editor as well. All we'll be using. We won't even be setting up or we won't need the runtime on this. So then, once that's done, you can actually generate the program. And then once that's downloaded, you can go over to OpenPLC. And to programs, choose a file, the one you just created, and upload. And then it'll compile. And once it's finished, you are ready to run. Okay, so now on to the HMI. You will have to build your own HMI with its own data sources. And so once you have logged in, and if you're experiencing issues with that, like a connection error, then I would go into your HMI box and run the startup command, which that can actually be found in the original documentation for exercise 1, right at the very end of part 3. It's like sudo /opt /tomcat6 /apache tomcat version /bin /startup.sh. But getting on into this, um, first we need data sources. We need data before we can actually do anything with it. So let me make this bigger. Okay, so we go over to the data sources tab. We can go ahead and power off the sources from the previous exercise, and go to this icon right here. Oh, first we need to select a Modbus IP and hit that button, and we can name it. So I'm just going to say exercise 3. I would set the update period to shorter, just because in transition you can actually be lagging behind because it hasn't refreshed. Um, and so TCP, change that to TCP with keep alive. Host is actually your IP of your PLC box. So for me, it's 10.0.2.15. So there's that. That's all the basics, and we can save. And if you are getting errors up here, or alarms, as they say, for all of this to actually be working, you need your board plugged in and your OpenPLC running, preferably with the program we just created, so you'll actually get correct values. Which actually, let me start that up so I don't get any of those errors. Okay, so then we go and actually use this, let's change that to green. And so now we actually want to read in data. So first, let's do our lights. We want to see which stacks are actually lit. And so the lights themselves are coils. And so for this register range, we want coil status. And if we read, so once we have our OpenPLC running, the way I found all of these registers is by going through and seeing what changed. So here we can see that this value is true. And this is actually our east-west value for yellow. And so if we read again, 0 is our red, 2 would be our green. And so there's green. Wait a couple seconds. There's yellow. A couple more. And there's red. And so once we have this, this number right here is our offset. So it just tells where to look for the value. And so we can go down here into coil status, offset 0, read result. We can get the result, and we can add a point. And so then we can name it. So east, this is for the red on the east-west side. So east-west red. And if you want to be able to remove the true status in the OpenPLC editor, you can leave this to settable, but I find that to be of no use since we already have it automatically starting. And so here we can see our red variable. And so there's the variable, and we can go back up here, change this offset to 1, add a point, name it east-west yellow, and change settable to no, save it, go back to east-west green, settable, no. So there's our variables for the east-west side for the lights. And so now, after a bit of research, I found that the physical, like the actual inputs on the board, are offset by 800. So here we can see our actual red light is true. So that's on. There's our green. There's our yellow. And there's back to our red. So if we go back down here and into the offset, into 800, and add the point, name, north-south, red, settable, nope, at that point, go up here, 801, north-south, yellow, settable, no, back up here, 802, name, north-south, green, and settable, no. So here we have all of our light variables. And we can go through and enable all points. And so we're actually looking for them. And at this point, we can actually go over to Graphical Views. So here we have the graphical view that we had last time. So for exercise 2. But when we need to go and to new view, create that. We can name it the same name as our data. And here we can actually select the background image. I'm going to go ahead and do this just because I have one pre-selected. Upload image. So there's our intersection. And now we actually want to add our lights. And so we need to go to binary graphic and the puzzle piece with the plus. And here's our data point. So if we roll over it with our mouse, we can see the name. At the moment it's unknown. But if we go to the pencil puzzle piece, we can actually edit it and add a point. And here we can see all of the variables we have access to, even the ones from last time. So let's just start with north-south. And we don't need to change any of that. And then we can actually go to the picture image set. I would recommend where is it? LED 24. It's a pretty good size. It can just be a little bit hard to find. I remember it being in between 16 and 48. It makes sense. Oh, well, we'll use LED 32 for now. And this is our red light. So 0 image. So when it's off, when it's false, we want it to be off, and when it's 1, we want it to be on. That is very big. LED 24. There it is. So red light on, off, and on. Oh, and that's the wrong orientation. So, and then we can just go ahead and do the same for all of the others. Okay, so now we actually have it fully visualized. So we can see north-south green light is on, then the yellow. Then as soon as it changes to red, green light on the east-west side is on, then to yellow, then to red. So there's the yellow, and we saw the red on earlier. And so if we go down and save, we can actually view it here. And so now we can go and add variables for our time, our timers. So go back to data sources. In exercise 3, hit the pencil icon. And these variables are in the MW location. So those are actually holding registers. And those start at offset 1024. So if we read, we can actually see these short numbers. And so these are the registers we're looking for. And so if we go back down to the point locator test, change this to holding register, offset to 1024, and add the point, name, so 1024 is MW0, and we put that for our green for north and south. So green time, settable is no, and the Modbus data type is a 2-byte signed integer. And yep, so save that, and it should appear over here, numeric and unactivated, with an offset of 1024. And so now we can go and 25, and that is our yellow for north-south. It is a signed integer and do not have it settable. 26 is our south red, signed integer, and just go through. And 27 starts with east-west green. And if you followed me, or it would be MW3 for the register, I believe. And then 8 is yellow. And 9 is our east-west red. Okay. So if we go over here and enable all data points, and then we can go back into our graphical view, go to exercise 3, and hit the pencil icon. We can edit. So we want, or at least I used a simple point as the component type. So if we add a point as our east-west green timer, and there's our timer. So this will begin counting down whenever north-south yellow turns on. And so we can go ahead and east-west red. So here, yellow turns on, green light begins counting down and transition. And just go through and add all of the points for the time. And so once all that's done, you can see the yellow timer is counting down, then the red timer and the green timer over there, and then the yellow timer here, and then the red and the green on the opposite side. So then we can save. And this is a completed version of the software side of exercise 3. So this is the physical part of exercise 3. It's pretty simple. You just need 3 wires, 3 resistors, and 3 LEDs, preferably 1 green, 1 yellow, and 1 red for simulating the north-south stoplight. So this is the completed setup for the physical part of exercise 3. We have 3 lights, each one with the positive side toward the board, so positive, negative, positive, negative, positive, negative, and with a corresponding colored wire going into the positive side from the board, and a resistor going from the negative side into ground. And so on the board, green is going into pin 12, yellow into pin 8, and red into pin 7. So if we go into our PLC and start it up, we should see that the green light turns on because we had set the virtual side to be red to be true, then the yellow, and then the red. And so now it's going into the virtual side. So if we go into the SCADA PR, you can see the yellow is on, and then the red, and back over, and there's the green on for the board. And that is a completed exercise 3.